So my name is Andreas Atle, and I work for Total here in Houston at the Research and Technology. I will present a long-going work for several years with a lot of collaborators. The two last ones here is Aurélien Caron that has been developing the code in OpenACC, and Pierre Jacquet, who is doing full waveform inversion. So I will come. Oops. Let me see here. So I will go through first a little bit different collaborators, and then I will describe why we want to use Digi, and I will also go through the formulation and so on. And then Digi is a little bit slower than finite difference, so we have a certain ways of speeding up as good as we can the code. And then I will go through, I will show a little, just a snapshot of a computation, and then I will show the work from OpenACC and full waveform inversion. So this is a collaboration, a project that started like 4 or 5 years ago, and we have a heavy collaboration with INRIA in France, with a bunch of PhD students, and also most of the VIEs, which are French long-term interns. It's an old military, French people can do military by moving abroad for a year or two. And we also have a collaboration with Tim Warburton's group when he was here at Rice, and also at Virginia Tech. With postdoc Jesse Chan. So most of the things that speed up the code origin from Jesse Chan, one way or another. And then we had a few more postdocs. Yeah, so why do we use discontinuous galerkin? So one reason is when you have topography. You see what I call the IPATI model here. It's very rugged surface, so it's very hard to use finite difference for this. And also we want to better resolve the salt boundary when we do Gulf of Mexico stuff, for instance. What more can I say? So we also one of the big problems with the elastic waves, you have a very bigger, what do you call it, range of velocities. So you have a problem with if you have a small shear wave zone, you have to resolve that with a very fine mesh in finite difference. But if you can have an unstructured mesh, you can utilize the unstructuredness. And I will come back to the effort to speed up here. So here I just showed what are the Digi formulation we are using. We have, this is the elastic equation, and you have derivative operators and lift operators and fluxes. And you have model, the model contribution, WC and W1 over rho. So if you use wedge, we will see that we can get better results at the end. And the boundary conditions are imposed weakly by either absorbing boundaries or free surface. And you can use a bunch of time integrators or time steppers. Euler we never use, but Adams-Bashford multirate, Adams-Bashford, RK2 and RK4. So far I call it high storage, what do you call it? There is an L-circ, low storage Runge-Kutta. We have the high storage Runge-Kutta so far. So sparse Digi operators, Bernstein-Bezier. So the standard implementation with the Digi uses nodal formulation, Lagrange basis functions. And then you get full derivatives. So there is a way of, so if you look at how do you get there? So this is the sparsity pattern of a derivative matrix. But if you use Bernstein-Bezier, you can reduce, you have a much better sparsity pattern. So the Bernstein-Bezier has sparse derivatives and enable higher order elements. Yeah. So, gosh. So you can see that with the nodal one, when we compute this 3D model here with for 1.2 seconds, with the derivative takes almost 2 hours, 1 hour and 50 minutes with the nodal. But when we implement it with the Bernstein-Bezier, it goes down to 30 minutes. And this is for elastic. And the flux and lift, it's 1.5 hours versus 55 minutes. So okay, I missed one thing here. So the model representation, originally we consider a constant model per element. And, but then if you have a blocky, it becomes a blocky model when you increase the order. So if you want to have higher order with P0, it looks very bad, like here. So we want to represent that with the weight-adjusted discontinuous galerkin. And if we, so it's a way to compute you want to compute the best representation when you apply a model to your wave field. You can do an L2 projection, and you get that is the so-called wedge operator. So this is one of the formulas. The A here takes you from number of degrees of freedom to the quadrature points, and M is the model defining quadrature points, and B takes you back to degrees of freedom. So for order P4, which is what I usually use, you have 35 degrees of freedom, but then you have to use quadrature that is at least exact up to 2 orders, because you take an integral of 2 basis functions plus the model. So usually we use 2p plus 1, and then you get 57 quadrature points. And it's possible to reduce that by introducing a little bit of numerical error in the quadrature. So with the nodal, the complete time step without applying the model takes 3 hours and a bit. Bernstein-Bezier is 124. But the model takes the same for both. And this is still the same amount of time that's for the previous. But you see the picture that when you increase the order, you resolve your model better and better. So one way we can utilize HP adaptivity. So we can change the order depending on your element size. So if you want a certain number of points per wavelength, there is a relation. You scale with H max, F max, and minimum shear wave velocity. To get the time step, you have the H min instead of H max. So to utilize this contradicting requirement, so to say, we can use the multi-rate time stepping. So you can divide you compute a heuristic time step for each element, and then you bin them, and every factor of 2, you have one level. So you can get the distribution of levels, and then I have a time stepping scheme that goes through for different levels, very complicated algorithm. It was actually someone from Rice, Zhang, who presented this at this conference a couple of years ago. So this we have implemented. Yeah, was it? So the current steps we have to do before we start to compute. We have to create an unstructured mesh, and that is probably the hardest part of the whole thing. It's not really, it has been a little bit of a struggle to get a good mesh. So we have an in-house code that produces meshes, and it takes VP, VS, and the salt mask, and also the topography. And then we reorder the elements so that the neighbors are close in memory. We prepare the high-resolution model with Python script. And we compute the variable orders. And we do compute the time step and multi-rate levels and so on. So, yeah. So here I have, how do I start this now? Here I have a computation with a snapshot. Can it be? I don't know how this. So, this is, I have 1.7 million elements, and it's 500 million degrees of freedom. And it's, here I just compute for 4 seconds on very many cores. We use Bernstein-Bezier, multi-rate time stepping with 5 levels. And we use constant order in this case, and the pressure source. So you see, on average, the derivative computation takes 55 minutes, 54 minutes. The flux computation plus the lift operator takes 1 hour and 34 minutes. And the model takes almost the same as the rest of the computation. Oops. So here, now I have computed here, we had an VIE last year with Yi that did an implementation using GPUs and OpenACC. So I have a computation with 5 nodes on our IBM system, Power 8. And we have, with NVIDIA P100, we have 4 GPUs per node. So you can see it's still 3D elastic, but I have taken a little bit smaller problem, so it goes a little bit faster. The nodal CPU takes like 600 seconds. Bernstein-Bezier goes down a factor 3. With GPUs, it's even faster, and Bernstein-Bezier CPU is significantly faster. One thing one can see here is that what I've written in red is the worst, and the green is the best. So I run a little bit too small problem on the GPU, so the communication is a little bit longer than it could be. So I upscaled, I solved the same with one node, so 4 GPUs. And then the communication goes from 707 seconds to 183 seconds. So, but I think during the internship, we had a lot of problems with the communication. So I think we can still improve that quite a bit. And finally, okay, I have a lot of time left. Finally, I will describe a little bit here the acoustic full waveform inversion we have used. There is a PhD student at India. So we are using full waveform inversion on unstructured meshes with the continuous adjoint state method. And that is a debate one can have if one should do the continuous or discrete. But for different reasons, we choose the continuous one. So we can use steepest descent, nonlinear conjugate gradients, BFGS, and so on. And what we do, this is in time domain, so we low pass filter the so-called adjoint source before you do the back propagation. And then we successively increase the frequency. So the first low-pass filter is at 4.5 hertz, and then we successively increase until 20 hertz. And in total, it's about 100 iterations or so. But we don't. This is very preliminary. It's more to see that the framework is working. And I can say that we also can invert for higher order models. But then you have to project back to Lagrange points, to nodal points, and that has some artifacts here and there. But we are convinced that the high resolution models, that the full waveform inversion is working. It's just a cosmetic thing at the end to visualize it. That is the problem. Yeah. So this is all I had to say. Thank you very much.
Sorry. Okay, so here you say about these quadrature points for representing the model. Apparently this, you get for order 6, you have 23 quadrature points. How does that come? Like, how do you get this number? Is that not the same as the...
We use optimized quadrature points. It's a German group, and we got the codes from Jesse Chan at some point.
So when you do this inversion at the is that the number of points will be based on?
Yeah, so you have the quadrature points as your model representation. So it's represented in the quadrature points.
So when you compute the gradients is also based on the quadrature points, or you based on your nodal points?
The gradient is based on the quadrature point, and that is why it's hard to visualize it, because you have to. We just took a least square fit, and then it was a little bit artifacty at certain places.
You actually have two sets of representation. Like the one is the nodal points for wave fields, and the one for the quadrature points for the gradient. So you actually have a projection between them. Is that right?
Yeah.
Okay.
Yeah, we don't project. It's only if you want to visualize it, but it's.
Any other questions?